alpha1plus.com.
Noses. They're a bit weird, aren't they? Sticking out from our faces, smelling stuff, making us snore. But did you know they're also vital in the fight against flu? The flu vaccine is the safest and easiest way to help protect your child, and it's completely painless. All it takes is a wee scoosh. Up the nose. Flu can be serious, so look out for your child's letter in the poster from school, and help beat flu with a wee scoosh. For more information, visit nhsinform.scot/childflu.
You are listening to Jambo Radio Scotland, online, on your smart speakers and on DAB Digital Radio in Edinburgh and Glasgow. You can download the Jambo Radio app now on Google Play and the App Store. Now it is time for the Science Show with Dr Dada.
Well, hello, and welcome to the Science Show with Dr Dada on Jambo Radio Scotland, broadcasting from the city of Glasgow. Today, as usual, we're going to be having a conversation. And the topic that we're going to be dealing with today is: how close are we to harnessing the power of nuclear fusion? We have a special guest, in fact, in the studio. And today we have Professor David Ireland. Now, Professor David Ireland is a prominent figure in the nuclear and hadron physics community, and he's from the University of Glasgow. He's renowned for his contributions to the understanding of the fundamental components of matter. We're going to learn more about that in the course of the show today and in the course of our discussion. So Professor Ireland leads the nuclear physics group and is also honored as a fellow of the Royal Society of Edinburgh. And today he will be sharing insights on nuclear and particle physics, and hopefully even on some of the recent breakthroughs in nuclear fusion. So join us as we explore this topic, and join me in welcoming Professor Dave Ireland to the studios.
Well, thank you very much, Adetunmise. That's a fabulous introduction. I hope to live up to it.
Yes, it's really a pleasure to have you in the studio with us today. And in fact, I think it's appropriate to say it's an honor to have you with us in the studio. I understand as the head of school, you have a very busy schedule, but to make out the time to show our audience that you actually care about us and really just share a thought or two with us is something that we really appreciate. Well, I'm your host, Dr. Adetunmise Dada, and don't forget you can tune in to our show via DAB. As mentioned earlier, it's broadcast in Edinburgh and Glasgow and surrounding cities. And of course, you can also listen and watch through our website, jamboradio.co.uk. And also you can catch us live and in color through our live stream on YouTube. Also, please do subscribe to the Jambo Radio Scotland channel on YouTube, and that way you'll get all the latest updates on our show. Again, today we'll be having our discussion of the question for the week, as we mentioned earlier, and you can join the conversation by calling this number. It is 0141 530 2787. That is 0141 530 2787. So let's consider one headline from the news, the science news in the world today. And this is something that's really related to our topic of discussion today. It's to do with nuclear fusion. And the title is Fusion Breakthrough at Lawrence Livermore. For those of us who don't know what Lawrence Livermore is, it's a national laboratory. So it's called LLNL, so Lawrence Livermore National Laboratory. It's a federal research facility in Livermore, California, and is primarily funded by the United States Department of Energy, established in 1952. So the news is actually something that we took from Nature, so Nature Journal. So there's a news piece there that says U.S. nuclear fusion lab enters new era, achieving ignition over and over. So this is about the repeatability of the process of the ability to carry out nuclear fusion. So the short bite there says researchers at the National Ignition Facility are consistently creating reactions that make more energy than they consume. So fusion reactions. So they have a net gain energy achieved. And this is quite interesting because the first time that they achieved the net gain was in 2022 in December. And they've successfully repeated that in 2023 and now again in 2024. So just a little description of how it works. We're going to hear a little bit more about that in the course of our discussion. But what they did is they directed 192 lasers to a tiny target containing hydrogen isotopes. And this was used to stimulate the conditions found in stars. So very high temperatures. And this led to the process of nuclear fusion. Now, they were able to demonstrate just by putting in 2.2 megajoules of laser input, they got 5.2 megajoules of power out. So that's the net gain in energy that we're talking about. So this is great news, isn't it? It's like, wow, nuclear fusion, that's the same process that powers the sun and other stars. But how far or how close are we to actually having this as a limitless, I've heard that word thrown around a lot, as a limitless source of energy in future? Well, we're going to see more about that in the show today. But that's a highlight from the news in the science world that we would like to focus on today's show. So now that brings us to our discussion with Professor Dave Ireland. So we're going to start with a series of sort of questions that hopefully will help us to get to know Professor Ireland a little bit better, and some aspects of his background and so on. So once again, welcome to the show. We warmly welcome you to the studios today, Professor Ireland. And to kick things off, could you please share with us what initially drew you to this topic, this field of nuclear physics?
Well, I guess it's quite a long story. I think one has to think right back to when you're a child, and that's when you start to sort of develop some passions about what's going on. And I guess one thing that's just run through is a feeling that I'd like to know how things work. Right. So, and that, you know, that could just mean taking something apart and seeing how moving parts put in. So, you know, you could take apart a bicycle and make sure that, you know, you understand all those pieces. But then you very quickly begin to wonder, what about all the other stuff around about you? And I just was probably fortunate enough to have had experience when I was younger to be able to have time to think about things. I seemed to get on okay at school. I seemed to be able to cope with mathematics, and that kind of naturally led into physics. And it seemed to me, that's quite interesting, and so on. And things like nuclear power at the time were there was probably a bit controversial, but there was sort of it was like, you know, it was a futuristic thing that was already here with us. So this was. The 1970s, so that dates me quite a bit. And at that time, there had been a series of nuclear power plants that had been developed over 20 years, but we were just getting to the point where nuclear power was very controversial. There were lots of concerns about the safety and how, you know, what would happen if something went wrong. So, you know, in that kind of background, it just felt quite good to, well, let's try and understand what it's all about. Yes. And then, you know, that was kind of my attitude. Once you know a little bit about the background, then you can have an informed opinion about things. Yeah. But so in terms of nuclear power, that's where I kind of started getting an interest in that. But generally, it is more a question of coming back to this thing about a childlike curiosity about how things work. Yeah. And fortunately or unfortunately, I don't think that's ever left me. I'm always kind of keen to find out how things are going on.
That's fantastic. Thank you very much for sharing that with us. And was there a particular event or maybe influence, maybe a person that really helped shape you in that direction?
Well, I suppose just over time there were a series of things like that. So what's quite interesting. So a lot of people will point to characters like Carl Sagan. You've probably heard of Carl Sagan. So he had this fabulous TV program called Cosmos, and that was one of those things you thought, my goodness, this is really tremendous stuff. I'd like to be sort of involved in that somehow. But at the same time, and again, this is really dating myself. In the 70s and 80s, there was a program called Tomorrow's World. And that was all about, taking technology at the time and seeing what might happen in the future. And it was done at a level that was very appealing, I suspect, to the general public. It wasn't too technical, but yet it was quite challenging to understand. And what is interesting, so that kind of I was excited about that. And many years later, I attended a meeting at the Royal Society, and the person that was delivering the material for the meeting was one of the presenters of Tomorrow's World. I see. And I was, oh my goodness, I was a real hero. You were a real hero of mine. So that was really nice. But I think I got to physics. So many of these kind of inspirations. One, I'm not sure if I should really say this, but my teacher at school had a drink problem, and sort of despite that, he was terribly behaved to a lot of students, and almost despite that, I still maintained an interest in physics. Wow. And actually, many years later, it turned out that from the same class, two of us ended up as heads of schools of physics in universities in the UK.
Well,
same class.
That hardly seems a coincidence, does it?
So I don't know what that says about the education system.
I'd say that teacher probably did a great job then. Who knows? Well, that's fantastic. So your primary school education, was that here in Scotland?
Yes.
I see.
Yes, indeed. Yeah. So I mean, I'm originally from the Borders region in Scotland, so it's a fairly standard Scottish education of primary, secondary. Yeah.
That's great. Fantastic. So primary school here in Scotland, secondary school here in Scotland. What about your university, like your first degree? Where was that?
Well, I moved all the way from the Borders to Edinburgh. Just 20 miles. So it wasn't too far. Yeah.
Oh, wow, that's great. So really made in Scotland then.
Yeah.
That's great. Fantastic. And then from there, you did a PhD. Was that in Glasgow or was it in Edinburgh?
So I stayed in Edinburgh for a PhD as well. But one of the things that was really appealing about doing, so I did a PhD in nuclear physics, and one of the things that was appealing about that was it's very international. By the time I started a PhD, there was almost no laboratory facilities for doing that kind of work in the UK. So we were sort of forced, we quite enjoyed going to international laboratories. And so that was really quite a good stimulus.
Yeah, that's great. Fantastic. I spent some time in Edinburgh as well myself, as an MSc student, and then I did my PhD in Heriot-Watt University.
Okay.
So yeah, Edinburgh. That's great. Good. That's something we have in common then.
Yes, indeed.
Very good. So let's change the gear a little bit, just for a little bit. We're going to talk a little bit more about the research that you do and the science that you do after the break. But before that, could you just give us a little taster on that? Was there any project or experiment that you found particularly challenging in your work? Is there anything that comes to mind that you find as a highlight in your career as that was a challenging experiment or project?
Challenging and those could be different things actually.
Of course.
I think so. It's as you know, because you've done a PhD. It's quite hard.
Yes. Yeah.
And I think the challenging thing is being faced with a lot of problems that there isn't necessarily an answer to.
True.
Which is a real shock compared to when you're an undergraduate or even at school, where science questions are answer this problem, and you answer it, and there's either a right or a wrong answer, and that's it. But then when you're faced with something that is, well, there isn't an answer to this, you're in charge of trying to find it out, or what have you. That's quite it can be quite upsetting, because you don't know whether you're right or not. But actually, even to get to the answers that you are interested in, you have a series of challenges. So in our case, you have to think of what experiment you're going to do. You're going to have to set it up, but you're also going to have to interact with many people who are all part of a team that allow the experiment to go ahead. Now, when I did a PhD, it was not a large team of people. It was maybe about a dozen people.
I see.
Sort of directly involved. But to some extent, for a young person who's starting out and it's their PhD project, you're sort of thrust into this role of saying, well, actually, I kind of need to tell people what to do.
Yes.
And that involves perhaps even senior people, certainly people who know much more than you do.
Yep.
And that is actually a different sort of skill to what you'd be learning as an undergraduate.
Yes, indeed. Wow, that's amazing. So did you do a postdoc as well after your PhD? What was between that and becoming the head of school? Just give us a short.
Yeah, quite a lot. So I was very fortunate to get a fellowship to take me to the Netherlands. There was a laboratory called, and it still exists, called NICHEF, which is their National Institute for Nuclear Physics and High Energy Physics.
Nice.
And at that time, they had an accelerator complex that was doing experiments. So it was one of the world leading ones, so I was really fortunate to get to work there for a couple of years.
Wow.
And then I moved back here for another postdoc position in Glasgow. Then the job as a lecturer came up, which was really quite fortuitous. I think I was sort of there at the right time in the right place. And I just like the idea of combining doing what I did for research with being able to teach as well, and I thought that was kind of the career that I would like to do. And again, a lot of luck involved, a lot of good timing and so on, but essentially it's just carried on from there.
So from lecturer, senior lecturer, professor, and so on. Good. Oh wow, that's fantastic. It's really a good thing, isn't it? A fellowship always helps in shaping the career path in academia, doesn't it?
Yeah.
Very good. Oh, thanks very much. That's fantastic. And yes, we're going to talk more science when we're back from the break. But now we're going to take a music break, and we're going to listen to a song by UB40, Cherry O Baby. We'll be right back.
Baby.
Well, that was Cheerio Baby by UB40. And this is the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting from the city of Glasgow. And we'd like to take this opportunity to shout out to our sponsor, our supporters on this show, and that includes IOP Scotland and the University of Glasgow, where I work and where our guest is from as well. And again, a reminder that you can listen to this show on DAB. So whether you're in the car, you're out in the garden, or wherever you may be, if you have a digital radio, you can listen to the show in Edinburgh and Glasgow and surrounding towns. And you can join the conversation as well. The number to call will be 0141 530 2787. Now let's pick up our discussion, our conversation from where we left it with Professor Dave Ireland, who's our special guest in the studio today. So perhaps we could continue by just maybe getting a little bit more into your practice as a scientist, your research. So some of the things that you research include nuclear resonances. Would you like to describe in, shall I say, broad strokes, what that means, what that's about?
I'll try.
Thank you.
So I think the place to start from, just very briefly, is to think about how do we understand any kind of matter that we see around us.
Yep.
I think possibly people might be familiar with the idea of an atom.
Yes.
So everything is built from atoms, and atoms react together, and they bind together into molecules, and the molecules interact with each other and so on. Now, in an atom itself, the way that we think we understand that is that it contains a very tiny but more massive piece in the middle called the nucleus. And it is very, very small compared to the size of the atom. Now, the atom itself is really, really small. We can't see them. They're too small to see. So we're really going right down in scale.
Yeah.
And so what we're interested in is something that's so small that we can't see it. So that's okay. So how do we know whether it's there at all, actually, or whether it's, or you know, what is it? Is it a point, or is it something a bit more tiny but still kind of got some structure? So what we can do is, instead of shining a light on an atom, we can shine particles of certain energies. Yeah. So I'm just trying to think of the example here. Our research quite often uses beams of electrons. So the very same things that go through the wires to give you electricity, if you can get them going through a vacuum and point them at a right target, and you give them enough energy, then they can begin by scattering off these tiny nuclei, and then the patterns in which they scatter off the nuclei tell you how these tiny nuclei actually look, what they're doing, and give you some sort of clue as to how they react. So over the years, I mean, this is a subject that goes back almost 100 years. People have been splitting atoms, but what that actually means is splitting the nucleus in an atom. And they've done that by firing particles, not just electrons, other particles as well, at these nuclei, and they break apart. So so the question is, I mean, sometimes people say that how do you understand what was in this nucleus before you broke it apart? And I've heard analogies like, you know, imagine you let a bull loose in a china shop, and then you got all the pieces afterwards, and you've got to work out what it was in the shop in the first place. And it to some extent that's sort of how it is, because it's really difficult. You've got to piece things together, and try and almost kind of guess, if you like, at how they react. So so that's why, you know, 100 years later, we're still sort of not quite sure what's going on, although we've got a better idea. Anyhow, so it turns out that atomic nuclei are composed of roughly speaking, two particles, one of which has got an electric charge in it and one of which does not. So the proton has got an electric charge and a neutron does not. And the thing that makes each nucleus different, which then ends up telling you which element you've got, which atom it is the number of protons and neutrons. So that's all fine. That's been known for quite a while. But then something a bit more subtle goes on when you try to contain something in a very, very small volume. What happens is that quantum mechanics takes over.
Yes.
And I know that's something that you're very familiar with, Tim, you see. So we're trying to think about how do we work out what's going on inside this tiny volume. And so what will happen is that any particle you put inside that is going to have what we call a wave function associated with it. Roughly speaking, that tells you, it gives you some idea of where it's likely to be at any one point. Now, the thing is that it would be really good if you knew what that wave function was for the individual protons and neutrons inside the nucleus. So quite a lot of what we've been doing, well, I say me as part of a large community of scientists for decades, has been to try to work out what these sort of wave functions look like and what happens when, two nuclei get fused together. So we'll come back to that when we talk about fusion, or when they break apart. And so one of the things you can do is you can shine a beam of electrons or even very, very high energy photons. So one of those two things at a nucleus, and the way that they scatter and the way that they knock out bits of the nucleus allow you to figure out what was the wave function of the protons and the neutrons before you had that interaction. So you get a feeling of what the structure is.
I see. Wow, that's really, really interesting. And the resonances, where do those come in?
So sorry, that's several stages.
Oh yeah, I know. It's quite like the resonances are quite an advanced already, aspect of it.
So I've mentioned protons and neutrons. So it turns out that that's not the full story. The protons and neutrons themselves have got some structure to them, and the best we can do for the moment is to consider them to be as if they're another scale down in terms of constituents. And we have this thing called a quark model. And in a proton and a neutron, we take it that there are three quarks that give most of the properties of these particles. Now, what happens if you've got any system with more than one particle in it and you bash it or give it some energy? Well, it's going to react. So either it comes apart or it sort of vibrates a little bit. It kind of rings, if you like. And it turns out that quarks have got this ability. We actually have never been able to see a separate quark before. They bind so strongly to each other that by the time you've put enough energy into them to break a proton apart, then Einstein's E equals mc squared tells you actually now there's enough energy to make more mass.
Right.
So as you pull these things apart with huge force, they come apart, but then you just get more protons and neutrons.
Great.
So you can't see the. So actually, this is one of the few cases in nature where what we're trying to do is we're trying to study a system where we're pretty sure that it has these sub-components, if you like, the quarks, but we can't actually pull them apart. Every other force of nature, you sort of know, I mean, the electromagnetic force, you can see individual charges and pull them apart. I mean, takes some effort, but you can do that. So that's one of the things that makes it fascinating, but it's also really tough because they're very resistant to giving up, the clues as to what they actually, how they work. And that's why we're still at this game for quite a long time, in the since it started. So a resonance is just this idea that you you give some energy to a proton or a neutron, and it resonates, right? So it goes, I mean, in quantum mechanical language, it goes to another state of energy.
Yeah.
And what we can see is, if we do our experiments right, we can see a spectrum of different energies at which there are resonances, and this is what's called a nucleon resonance. And for many years, the model that we thought was really explaining everything, the quark model, predicted a lot of these resonances, except we didn't see them all. Now, I think, I mean, part of the reason is it could be just really difficult to see them, because, as I said, they don't give up their secrets very easily. Or we've got the model wrong. So it's one of those two things. And so that's one of the things that is really quite stimulating, is it actually, by almost proving something is wrong, then we make a leap to a potentially better understanding.
Wow, that's really interesting. So now we understand what the missing resonances are about. Some of the other terminologies have been explained as well. We know what the protons are, and we know what a nucleon is. A nucleon would be either a neutron or a proton.
Correct. It's a collective name for them. Yeah.
Good. Wow, that's fantastic. And what about the approaches that you use in your science? So you use a lot of statistical physics, and could you tell us about that? What does it involve? Is it mostly analyzing experimental data, or do you do experiments yourself, like your team? Do you do these experiments as well?
So all of these experiments take a large teams of people. The particular collaborations I'm in maybe have a couple of hundred people involved. And that's because, sort of paradoxically, the smaller the thing you want to study, the more energy you need to put in. And the more energy you put in, the more the stuff that comes out is sprayed around the place, and the bigger the detector and the more sophisticated a detector you need. So you need a whole array of people, right from the people that understand how to accelerate beams of particles to people that build you the targets at the other end. That's not a simple thing either. And then you've got a whole range of different types of detectors that need to be built at the end. And sometimes you put detectors in that are quite different, and they're all part of a whole system, and they have to kind of be connected together. So that's fine. There's usually a team of people that manage to do that, and then of course you need to run the experiment. And in our case, a lot of the experiments take weeks and months of just kind of doing a similar thing all the time. But unfortunately, what happens is that things will go wrong.
As experiments, that's experimental physics for you, isn't
it? Exactly. So maybe there's a thunderstorm outside, and the local grid of power slightly dips in energy or what have you for a tiny fraction of a time, but that then means that one of the pieces of equipment that's monitoring your experiment just sort of fails for a bit. So somebody has to sort of stop what they're doing. They've got to go and reset, and then so you've got this whole range of things that might happen during an experiment, and a lot of what you do during an experiment is to try to kind of control all of those things that you hadn't really predicted beforehand. And at the end of it, you get left with a lot of data, which are basically just the signals coming out of the detector. They're recorded in some medium or other. I mean, we can record them straight to a kind of computer disk nowadays, and that's fine. It's just signals that are numbers. And so then you've got the problem of interpreting them all. And so that's when the statistical bit comes in, because you've got to first identify. If you imagine there's a stream of beam particles come into a target, and each one of them might interact with the target or might not. So it would be good to know the exact point in time that an interaction happened. So you need to have
Yes.
that. You need to be able to do that, and then you need to be able to say, well, if I know when that interaction happened, which are the particles that have come out were came out of that very interaction.
Yeah.
And so that involves you trying to pick out. So you need to first of all identify the type of particle you've got in the detector, and then say, well, was it related to the interaction that I'm interested in?
Yep.
And that involves you doing what are called coincidence measurements. So you get signals from different detectors, and they're there at the same time, effectively.
I see. Wow, that's interesting.
So once you've got that, you just have this series of events, and it could be billions of events. And you've got to go through them painstakingly and say, well, look, I'm interested in that one, but not those ones. And you put all sorts of conditions on it. And in the end, it is like looking for a needle in a haystack.
Yeah.
But what you try to do, what the skill, I suppose, is knowing how you're going to go through the haystack and discard a lot of the hay that you know the needle's definitely not there.
Yeah.
And then you know, when you home in on the thing that you're interested in, then you have to say, well, that's probably what I'm interested in, but I can't be 100% sure. So you have to have some idea of how certain you are that this is the thing you're looking for.
That's interesting. So that's where the statistical mechanics comes in,
Yes.
conditional probabilities, Bayesian methods, and so on.
Yes. Yeah.
Interesting. That's fantastic. Well, we could go on and on about this, couldn't we? But I think the time has come now for another break. Now we're going to listen to a song, an Afrobeat song, entitled Laye by Kiss Daniel, and we'll be right back.
Boy, Kiss Daniel. I know I'm crazy, but this is all I afford you. Fuck you, baby. In a power, miss you. Girl, I'm feeling you. I'm feeling you. Hey, turn around, my baby. See your flash. Everything I give to you, girl, I don't want it back. Say I'm ready to be yours forever. No another. Say don't you worry, girl, they can't take me away. Baby, go try. I just wanna let you know. I just wanna let you know. Baby, go try. I just wanna let you know. Baby, go ojo. Baby, go try. See, I just wanna let you know. No girl can take me away. Baby, go try. Go see Rurelo, baby, say go ojo. I know I'm crazy, but baby, take my Kikia, my dear. Baby, I'm not ashamed to show you off. Baby, show me more. Yeah, oh. Turn around, my baby, see your flash. Everything I give to you, girl, I don't want it back. Say I'm ready to be yours forever, no another. Say don't you worry, girl, you can't take me away. Baby, go down. I just wanna let you know. I just wanna let you know.
Wow, that was fantastic, wasn't it? That was Laye by Kiss Daniel. Very danceable track it was. And this is the Science Show with Dr Dada on Jambo Radio Scotland, broadcasting live from the city of Glasgow. Again, we'd like to shout out to IOP Scotland for supporting this show. And we'd like to remind you to listen to us on various platforms. We're on Facebook, Instagram, Twitter, or X. And you can reach out to us on jamboradio.co.uk, and you can also follow our channel on YouTube. Now we've come to the part where we'll talk about the question for the week. And this is a very, very interesting question, especially in these times when we're talking about, net zero, and we're talking about the energy crisis. And the question is, how close are we to harnessing the power of nuclear fusion? So we'll talk a little bit about that and other applications of nuclear physics as well. And you can join the conversation by calling 0141 530 2787. Once again, that's 0141 530 2787. So how close are we to harnessing the power of nuclear fusion? So I'll ask the expert in the studio, Professor Ireland. What would you say about that?
So there is a kind of ongoing joke that nuclear fusion as a power source is always 30 years in the future, no matter when you say that. I'm not sure that really has changed. I think what you were talking about earlier is definitely, technologically, these kind of experiments are incredibly sophisticated.
Yes.
They involve immense amounts of energy that go in, and then obviously immense amounts of energy that come out. But it's so difficult. It is, as you said, it's trying to harness the same thing that's going on in our sun. And that's quite big and quite heavy, and it does it because it's so big and heavy, and it compresses all the matter in there because of gravity. Exactly. Now, it's been going for several billion years, so I think if somebody says an unlimited source of energy, then okay, that's not unreasonable because you've got something that appears to be around for quite a long time. So maybe for all practical purposes, it might be unlimited. But the basic problem is that how do you contain this stuff? So when these reactions go on, they're not chemical reactions, they're nuclear reactions, and the energy that's released is so much that any power station, really, all you want to do is get a source of energy, heat some water up, boil it, and get that to turn a turbine to allow you to create some electricity from it. And really, a fusion reactor or even the fission reactor are no different to that. They're just a source of heat. But what you want is that what you put in is much, much less than what you get out. And the problem is containing this stuff. It's a form of matter called plasma, and that's really difficult, especially at such high temperatures. So you can create it by, as you said, really focusing lots of lasers at one tiny little point. To contain it is a bit more difficult. Some plasmas can be produced that you can contain in a kind of, they're things called tokamaks reactors. So they're like a donut shape. These are really big sort of devices, and in principle you can contain a plasma in one of those because you don't want it to touch anything. It's so hot that if you touch anything with the plasma that's fusing, it'll just melt it. So just
vaporize.
If it's a bit like you've got a chemical like an acid that it's so powerful that it burns through things. That's what's causing all the difficulty, or has for many decades.
Wow, that must be really challenging indeed. So that's a very good perspective on that question. How close are we to harnessing it? I really like that. Thank you very much for that. And when it comes to some of the breakthroughs that we've heard of in the news, so they say nuclear fusion, And someone who's not really, doesn't have a scientific background might think, well, what about the nuclear power plants? What's new about this? What's the difference between this nuclear fusion and what goes on in the nuclear power plants?
It's a great question, and I'm sure it gives rise to a lot of confusion. So the existing nuclear power plants operate. They create heat. I mean, most power plants just create heat somehow.
Yeah.
They create heat by a process called nuclear fission.
Yeah.
So that is where you take very heavy nuclei, very heavy elements. So uranium is an example, and if you break that apart, then what then happens is that it's our friend the neutron again. It breaks into some neutrons, which then go on to break apart more uranium nuclei, and each of those, as they sort of, if you don't control it, it becomes what's called it is a chain reaction. And you have to control that, because if you don't, then you get an explosion.
Meltdown.
Yes, exactly. Now you can control it in a reactor. And that has been known about and been harnessed for 50 or 60 years, probably even longer than that. As a source of heat, as a source of energy, it's kind of well known. And I think what I was getting at before with the difficulty in constraining the fusing plasma, that's the difference really is that fission breaks apart a heavy nucleus.
Yes, fusion.
And fusion pushes together very light nuclei. It doesn't sort of sound right to begin with as to why you get one and not the other, or the other way around. But it's just a sort of fact of nature, if you like, that you if it's very light nuclei, or even just protons themselves reacting with each other, you tend to get a lot of energy out of them pulling themselves together, so they're fusing.
Yes.
Whereas if it's very heavy nuclei, the energy comes from breaking it apart.
Yeah.
And so you might think, well, wait a minute, what's going on? Why is one not? So the thing to think about is that there's an element sort of in the middle, which is iron, just everyday iron, which it's kind of the bit that you stop gaining by fusing anything and you start gaining by fissioning. So it's like a curve where iron's kind of at the top, and either side of it are the bits that you want to be playing with.
I see. Wow, that's interesting. So obviously fusion is a big deal. It seems to be more environmentally friendly as a source of energy, doesn't it? But maybe we can move a bit away from the energy and talk about other maybe practical everyday applications of nuclear physics. Is there anything that comes to mind that you'd like to share with our audience?
Well, I mean, there's quite a lot of applications of nuclear physics that have been around for a while. I suppose in the medical sphere, we have ways of investigating issues with patients. So medical scanners, a lot of medical scanners have come from nuclear physics research. I mean, even an NMR scanner, it used to be called, nuclear magnetic resonance.
Yeah.
You call it MRI now, because the word nuclear wasn't particularly good for patients.
Yes.
But that all came from similar research. And of course, people will know that conditions, if somebody has cancer, they're quite often treated with radiotherapy. Yeah. And again, that's using the energy from radioactivity to kill the cancer cells. And the other side of it is, though, so you want first of all to give the therapies, which are sort of basically doing the job that a surgeon can't do. And then you also want to trace what's happening with them. So you get other kind of scanners which allow you to put tiny amounts of radioactivity into patients. But if you've got it right, the kind of biological molecules that the radioactivity is attached to will go to preferentially to sites that you're interested in.
I see.
And you will be able to pick up from the image of radioactivity where they are. So you might be able to pick up that somebody has a tumor or something else going on. So that's probably the most obvious example.
I see.
A less obvious example, but probably everybody has one, is a smoke alarm. Smoke
Nice.
alarms are tiny little bits of radioactivity that will I mean, it's so small that it never harms anybody.
Good. Good to know.
I mean, I don't want to start mass panic or anything like that. But I mean, basically, if you go out into the street, if you're or even sitting in this building, all the time we have tiny trace amounts of particles coming at us from the rest of the universe. We can't stop it. We can't help it, and it actually doesn't do us any harm. But interestingly, workers in my research group have been able to harness that, because what then happens is these are particles that originate as protons from the rest of the universe, but when they hit our atmosphere, they sort of react with our atmosphere, and by the time they reach us on the ground, they're muons. That's a different particle name there, but
I see.
so the idea is that those muons are a bit like electrons, our friendly electron, but they are a bit heavier, and because they're going at quite high speeds, they can go through things a little bit more so than X-rays.
I see.
So if you imagine that what an X-ray gives you on like a medical image where you can see bones and other structures, muon imaging allows you to go through things that are much thicker. So if it's something that's encapsulated in concrete, for example, you might be able to see bits of metal in there. And so that's one of the things that we're kind of interested in developing, is how to detect things within concrete and other structures.
Wow, that's yet another application, isn't it? Oh, that's fantastic. Thank you very much. Yes, I'm afraid time is going very fast because we're having so much fun talking about nuclear physics. But before we go today, would you like to say something about the School of Physics and Astronomy, where you're head of school? Imagine your audience is a group of young ones who are thinking possibly about doing physics in, a university in Scotland. What would you say to them about the school?
Well, I mean, there's a lot to say about the school. I'm hugely privileged to be head of the school, and there's a lot of great work that goes on. I mean, I think the thing is to try to encourage people to want to study the subject in the first place. So there's a piece about just enthusing about physics as a subject.
Yes.
But then also to say, well, in any university department of a subject, what you'd like to see is that there are people at the forefront of research. That might be something that would be interesting.
Yeah.
And so all of our research groups have programs of research that involve top level scientific understanding of things. Yeah. It's from the very big, so looking at the structure of the universe, and we have a team involved in looking at these strange things called gravitational waves, and then down to the very smallest, which are the smallest particles. I mean, I've mentioned quarks, but there's a bit of a layer beyond even quarks. There's other things in there as well. So we go from the very small to the very big. And if you are interested in that sort of way of thinking, finding out how the universe works, do physics, absolutely. And coming to our school, you will encounter people who have equal passions in that area, and would probably like to get you involved in their work.
Fantastic. Thank you very much. Yeah, that's about all that time will allow us to do today on the Science Show with Dr. Dada. It's been a real blast, hasn't it, with Professor Dave Ireland talking about nuclear physics and all these various applications. Just one joke then, because we promised we were going to share jokes, but we'll share one. What did the nuclear physicists have for lunch? Any ideas?
I think I know the answer to this.
Yes, go for it.
Nuclear fish and chips?
Yes.
Very good.
Fish and chips. Good. Anyway, that's all that we can take today. And we'd like to thank everyone for tuning in. And this is Dr. Dada signing out on The Science Show. Stay curious.